Hi there and welcome to Olagold Academy. Now, for today, we're considering a topic known as dimensioning in physics. Now, what is dimensioning? Dimensioning refers to how various physical quantities relate to fundamental quantities, especially mass, length, and time. Dimensioning refers to how various physical quantities relate to fundamental quantities, especially mass, length, and time. Especially mass, length, and time. Now, if we say dimensioning is just about relating physical quantities to fundamental quantities, which in most cases is usually mass, less, and time. If you're asked to dimension any particular physical quantity, they're asking you to relate that particular physical quantity or express the physical quantity in terms of mass, length, and time. Now, I said that dimensioning refers to how various physical quantities relate to fundamental quantities, especially mass, length, and time. Now, what are physical quantities? Physical quantities are those measurable properties of an object or of a body. Physical quantities are those measurable properties or qualities of an object or of a body. Now, in the definition of dimensioning, I also mentioned fundamental quantities. Now, what are fundamental quantities? Fundamental quantities are those quantities that cannot be expressed in terms of other quantities. I have defined physical quantities. I have also talked about fundamental quantities. Fundamental quantities. I said that fundamental quantities are those quantities that cannot be expressed in terms of other quantities. Now, the units of fundamental quantities are referred to as fundamental units. The units of fundamental quantities are referred to as fundamental units. Now, these fundamental quantities forms the basis for dimensioning and also dimensional analysis. I repeat, these fundamental quantities forms the basis for dimensioning and dimensional analysis. Now, there are seven fundamental quantities. There are seven fundamental quantities, and their units and their symbols I'll be giving out on the board right now. We have fundamental quantities, we have fundamental units, and we have their symbols. We have their symbols. Now, the first one, we have mass. The fundamental unit is kilogram. Kilogram. The symbol is kg. Number two, we have length. The unit is meter, and the symbol is n. Number 3, we have time measured in seconds, and the symbol is small s. Number 4, we have temperature, and it is in Kelvin, and the symbol is K. Number 5, we have electric current. The symbol is ampere. The unit is ampere. The symbol is A. Number 6, we have amount of substance. We have amount of substance, and the unit is mole, and the symbol is MOL. Lastly, number 7, we have luminous intensity. And the unit is candela. The symbol is CD. So these are the fundamental quantities we have, their units and their symbols. Now the next thing we are dealing with is what are derived quantities now. Now, derived quantities are those quantities that can be expressed in terms of other quantities. Their units are referred to as derived units. An example, we have velocity, we have speed, we have acceleration, we have mass, we have force, we have work done, we have stress, we have strain, we have Young modulus, and so on and so forth. Now, let's consider the dimensioning of physical quantities now, of various physical quantities. Dimensioning now. Now, the first physical quantity we are dimensioning is speed. Now, listen attentively. Before you can dimension any particular physical quantity, you must be able to define that particular quantity. Now, how do you define speed mathematically? Speed is expressed as distance over time. Speed is distance over time. Now, if you check distance, remember, dimensioning is just about expressing physical quantities in terms of mass, length, and time. Mass, length, and time. Now, among the categories we are having here, what category does distance fall to? Distance falls to the category of length, because distance is a kind of length. So you can express distance as equal to length. So the dimensional unit for distance is L. So how about time? Time is what? Expressed as what? The capital C. That's it there. Now, next thing we are going to have, from here we can have this length times 1 over T. If I segment T out, I will have length times 1 over T. Now, what is the index form of 1 over T? It is what? T minus 1. So we are going to have this L is power T, LT is power minus 1. So this becomes the dimension for speed. Number 2, we have velocity. So we are dimensioning velocity next. Now, how do you define velocity? Velocity is expressed as displacement over time. So we have displacement over time. Now, displacement also is a kind of length, because we define displacement as distance traveled in a specified direction. So displacement is also measured in meters, and the dimensional unit is length. So we have length. Time is also t. So we can have, since we have this, we can also have this also. You give us this lt minus 1. So as we can see that both speed and velocity are having the same dimension. So we can say that they are dimensionally homogeneous, or they have dimensional homogeneity. Now take note, any physical quantity that has the same SI units will always have the same dimension. For instance now, speed and velocity are the same SI unit, which is meter per seconds. So they will have the same dimension. Stress and Young modulus have the same SI unit, which is Newton per meter square. So they will also have the same dimension. Take note of that. Now, the next physical quantity we are dimensioning is acceleration. Acceleration. Now, how do we express acceleration? Acceleration can be expressed as velocity over time. Now, velocity is already expressed here as lt minus 1. So we can have lt minus 1 over t. So we have this. From here now we can have this lt minus 1 multiplied by 1 over t. From here now you can have our lt minus 1 multiplied by t minus 1. So in indices, if we have two particular quantity or two particular numbers or two particular variable multiplying each other, what do? We add their powers. So we can have lt minus 1. Now minus 1 plus minus 1, we get what? Minus 1 minus 1, which give us what there? Minus 2. So we can have what? lt minus 2 as the dimension for acceleration. So we have lt minus 2 as the dimension for acceleration. Alright, the next one we're dimensioning is force. Alright, the next one we are dimensioning is force. So how do we define force? Force is defined or expressed as mass times acceleration. So you have mass times acceleration. Now mass is expressed as capital N. Because I explained that mass is expressed as capital M during the definition of dimensioning. Now what is acceleration? Acceleration has already been dimensioned as lt raised power minus 2. We have lt raised power minus 2. So it becomes mlt minus 2. So this becomes the dimension for force. So the next one we are dimensioning is area. Number 5, we have area. Area. Now, how do we express area? We express area as length times breadth. So we have length times breadth. Now let's not forget that breadth is also a kind of length, but it is a shorter length. So breadth is a shorter length. And remember, we're expressing them in terms of mass, length, and time. So we're expressing breadth here as a kind of length. So we have length. From here we have what there? L square. So this becomes the dimension for area. The next one we are dimensioning is volume. Number 6, we have volume. Volume. So how do we express volume? Volume is expressed as what? Length times breadth times height. So this becomes, so breadth is also a kind of length. So replace length with breadth. Height also is a kind of length. So replace height with length. So we have L cube. L cube. So L cube becomes the dimension for volume. The next one we are dimensioning is density. We have density. Now density, the unit for density is rho. We have rho to denote density. Some write it this way. They are both rho. They are rho, not P. This is P. This is P. This is rho. That's the symbol for density. Alright. So density is expressed as what? Mass over volume. So you have density as mass over volume. Now what is mass? Mass is what there? Capital M. Volume is what? N raised to power 3. So what next? We can have our n to be multiplied by what there? 1 over L raised to power 3. So the index form of this is what? We have what there? M times L raised to power minus 3. Finally, we have what there? ML minus 3. So this becomes the dimension for density. This becomes dimension for density. The next one we're looking into is pressure. Number 8, pressure. Now, how do we express pressure? Pressure is expressed as what there? Force over area. So you have force over area. So this is dimension for, this is the expression of pressure, force over area. Now what is force? Force is expressed as what there? Mass times acceleration. So we have this mlc minus 2. Area is expressed as what there? L squared. So we have L squared. From here we have what there? mlt minus 2 multiplied by 1 over L raised to power 2. So this one becomes, the index sum of this becomes mlt minus 2 multiplied by L raised to power minus 2. Now, if the expression is much more further, we're going to have to be equal to m. We have two base multiplying each other, so we take the what? We take the power. The power of L here is 1. Anything that is standing alone is raised to the power of 1. So the power of L here is 1. So 1 plus, this becomes plus in indices. 1 plus minus 2 becomes what there? 1 minus 2. We have 1 plus minus 2 becomes 1 minus 2. So guess what there? Minus 1. So it becomes ml minus 1 What next? T minus 2. That's it there. So we have from here we have this. So this is the dimension for pressure. ml minus 1, sorry, ml raised to the power of minus 1, C raised to the power minus 2. The next one we're looking into now is discharge. How do we express discharge? Discharge is rate of change of volume. Discharge is rate of change of volume. Now, if you see rate in pieces, it means that thing divided by time. So rate of change of volume means volume over time. So we have volume over time. Now, what is the dimension for volume? Volume is expressed as what there? L cube over time is what there? C. So what's the next thing there? It becomes L cube multiplied by T raised power minus 1. So it becomes L cube T raised power minus 1. Number 10 is, let's look into work done. Work done. How do you express work done? Work done is defined as what? Is expressed as force times distance. Force times distance. Work done is expressed as force times distance. Remember, we have expressed force earlier. Said force is what there? Mass times acceleration times, what is distance? Distance is expressed as what there? As L. What means we have what there? MF. 1 plus 1 give us what there? 2. So we have T minus 2. So this becomes the dimension for work done. ML squared T is power minus 2. Now, number 11, let's look into power. We have power. How do we express power? Power can be expressed as work done over time. Work done over time. Now, what is work done? Work done is already expressed as ml squared T raised power minus 2. So we have this ml squared T raised power minus 2 over time is what there? T. So we have this. Alright, what next? We have ml squared T raised power minus 2 multiplied by 1 over T. And the index sum of this becomes T raised power minus 1. So I can express this one as what there? T raised power minus 1. It becomes equal to, we have L squared. Next, we have minus 2 plus minus 1 becomes what there? Minus 2 minus 1 give us what there? Minus 3. So we have ml squared T raised power minus 3. This becomes the dimension for power. The next one we are looking into is stress. Now, stress can be expressed as force over area. Force over area. Now, how do you express force? Force can be expressed as what there? Mass times acceleration, which is what there? Mass times acceleration. Area is what there? L squared. L squared. So what next? We have MLT minus 2 multiplied by L is power minus 2. So what next? We have what there? ML 1 plus minus to give us what there? Minus 1 T minus 2. So we have this as dimension for stress. ML is power minus 1, T is power minus 2. If you notice that pressure has the same dimension as stress, so you can see that pressure and stress are dimensionally homogeneous, or they have dimensional homogeneity. Now let's look at strain. Now, how do we express strain? Strain can be expressed as elongation or extension over original length or over length. So we have elongation over length. Elongation over length. Now, elongation is also a kind of length because this stress are expressed under Hooke's law. Now, I will try to make a video on elasticity where we explain Hooke's law, we explain stress, we explain strain, and we explain Young modulus. So elongation is also a kind of length. So length is expressed as what there? Meter. So we have what there? So meter is expressed as what there? As length. Length also as length. So what happens? Length cancels the length. So we have what there? We have 1. So as you can see that strain has no dimension. So we can say that strain is a dimensionless quantity. Strain is a dimensionless quantity. Next one we are looking at is Young modulus or Young modulus. Now, Young's modulus can be expressed as what? Stress over strain. Stress over strain. Now, stress has already been expressed as what there? ML minus 1 T minus 2. Now, what is the dimension for strain? Dimension for strain is 1. So we can say that the dimension for Young's modulus is also ML minus 1 T minus 2. As we can see that pressure, stress, and Young modulus are dimensionally homogeneous. They are dimensionally homogeneous. Next one we are looking into is energy. As we all know, energy is measured in joules. Work done also is measured in joules. So what happened there? Since they have the same SI units, they will have the same dimension. Now, what's the dimension for work done? Work done and energy have the same SI unit, which is joules. So they will have the same dimension, which is ml squared t is power minus 2. The next one we are looking into now is viscosity. We are expressing viscosity. Now, viscosity can be expressed as what there? The ratio of force over area times velocity gradient. Velocity gradient. So we have this. So this is dimension for force. This is the expression of viscosity. Viscosity is expressed as the ratio of force to the product of area and velocity gradient. Now, what is velocity gradient? Velocity gradient is same thing as velocity over length. This is velocity gradient. And velocity is expressed as what there? LT minus 1. Length is expressed as what there? L. So what happened there? L cancels L. So the dimension for velocity gradient is what there? T minus 1. So we have what there? Alright. The dimension for force is MLT minus 2 over the dimension for area is L squared multiplied by the dimension for velocity gradient is what there? T minus 1. So we have this. Alright, so if we take the inverse of this, it becomes ml t minus 2 multiplied by L squared t minus 1 raised power minus 1. So we have this. So this one here becomes the inverse of this. So we have L squared times L squared multiplied by 3 raised power minus 1, everything having an inverse. So expressing this bracket, we are going to have ml t minus 2 multiplied by L 2 times minus 1 give us what there? Minus 2. T, the power of t is minus 1. Minus 1 times minus 1 give us what there? Ordinary t. So what next? We are going to have one here plus minus 2 here, which gives us 1 minus 2. And that becomes what there? L power minus 1. Now, minus 2 plus 1 here give us what there? Minus 1. Minus 2 plus 1 give us what there? Minus 1. So this becomes the dimension for viscosity, which is eta. If you find this video helpful, do well to hit the like button, subscribe, and turn on the notification bell so that you can be notified whenever I release a new video. Do not forget, this is Olagold Academy. Like, drop a comment, share, and follow for more. Thank you.